Hi, Philip, and hello, everybody. Welcome back. It's just another minute until we get to 2:20, and then we'll just get started. But for now, good to see you guys, and hope you're all doing well. Cool. Hi, Corey. And hey, Nathan. Okay, guys, and hi, Remy. Good to see you too. All right, let's just get things rolling. Good to see everyone once again, as usual. Hope you had a good weekend and everything's going well in your other classes and just in life overall. So let me just make sure everything's clear on a couple of upcoming meetings and dates. All this is listed in the syllabus and the schedule that you see there too, but I'm just going to try to make sure that we don't lose touch with some of the key dates that are coming up now. So this week, today, we're going to have the lecture part 2 on chapter 12. We did part 1 of that last Thursday, so chapter 12 covers 2 meetings, Thursday last week and today, Tuesday today. And then Thursday, next class period, you're going to take your last quiz on chapter 12. So that's quiz 3. It's just on chapter 12. It's just on the topic of science. So Thursday, 48 hours from now, you'll be taking that quiz. And as before, the quiz is not going to be a class meeting like a live stream on YouTube. So you're just going to have that for our Thursday meeting this week. And I'll send you the quiz form through Canvas just before our official class time. And like before, you'll have that same window of time to complete it before 3:45 and just send back your responses to me. So that's the third quiz that's coming up. Also, as you guys know, you just submitted the third homework on fallacies, fallacies in advertising and marketing. And so thank you for doing all your work. I appreciate it. I'll be grading those through the week as well as this upcoming quiz, and I should be able to finish all that throughout the remaining part of this week. Afterwards, after you take this quiz on Thursday, next class, then the next upcoming thing is that there's just one more homework assignment and the final. So we're getting closer to the end of the semester. I will give you the instructions on homework 4 after you take the quiz, because I just kind of want you to be able to focus on the quiz for the moment. But it's not due until 2 weeks from now anyway, that fourth homework. So you're going to have plenty of time to complete it. And we'll just hold off for the discussion of homework 4 until we get past this chapter 12 and the science quiz. Other than that, I'm going to give you guys a study guide during week 15 or the weekend before that. And that study guide will just give you a sense of all the topics that we will cover as we go through our review sessions and all the topics that we've learned through the semester. And then you'll have your final exam, which is the last day of class. That's Thursday, May 27th. So anyway, just a kind of long story short, you have a quiz on Thursday this week, 2 days from now. That's just on chapter 12, science. Then you have your fourth homework. That's going to be due May 18th, 2 weeks from now. And then you have your final exam. That's May 27th, which is a little over 3 weeks from now, because today's the 4th. So just keep those things in mind. And as always, be in touch with me through email. If there's anything you want to know about your grade, your scores, checking in on anything, please email me, and I check those messages each day, and I try my best to be pretty timely the way I respond. Okay then, guys. So hopefully that's all clear, and if not, if there's anything that you want me to repeat or to just go over and comment on more or explain more, then just let me know anytime in these comments that you're leaving in the chat. Okay, so then, let us return to our current chapter of the book. That's chapter 12. And chapter 12 is all about science. Sorry. Okay, so what I'll first do is just kind of review some of the topics on Chapter 12 that we covered on Thursday last week. Briefly just go over those quickly, and then we'll talk about the material from there that we didn't get to. So as you know, Chapter 12 is about science. We started this chapter with just a general base definition of what science is. And science is when you reason from observable facts to testable explanations for the facts. So in science, we start with observation. We're here in this world and we observe things happening. We identify data, we identify events. And with science, we want to know why those things have happened. We want to be able to explain the cause that led to those events that we observe. So there's so many things that you can observe, whether it is a volcano happening, a lightning bolt happening, a disease that is passing through the community, a solar eclipse, lunar eclipse, properties of different chemicals in the periodic table of elements, how they react with each other. In any of these different cases, we might observe something, but then we want to know why it happened. As a scientist, you don't just look at the volcano and say, wow. You want to know why. What is the cause behind that, so that we can have a better knowledge of it, so that we can mitigate it, understand when it's likely to happen, or control things. So science gives us the ability to understand the reason behind observed events. And when we get those explanations, we provide a test that allows us to verify that they're true. So science gives testable explanations for observed facts. Then we talked a little bit about who are some important figures in the early history of Western science. And there's a lot of names that could be put on the table, but we really went with two that were mentioned in the book and highlighted in the book. One important early figure of Western science was Nicholas Copernicus. So he was a Polish astronomer who lived from 1473 to 1543. And maybe somebody remembers what his big discovery was? Tell me if you know, someone here in this chat. What did Nicholas Copernicus discover? It's considered a revolutionary discovery. Some people think that it launched the scientific revolution. What was it? Anybody know? Let me know. Just, touching base with you. Sometimes it's nice to get the little interaction and feedback. So, yeah, Copernicus made a major discovery. What was that? Someone knows. Someone will let me know. The heliocentric model of the solar system, correct. Now, can anybody tell me what heliocentric means? That's correct, yes. But, just asking a follow-up question now. What is the heliocentric model, in other words? Define that. Heliocentric, big word. What does it mean? Hi, Land, good to see you. Land, do you know what it means? The heliocentric model of the solar system, what is it? But not just you, anybody. Since I just saw you there, though, throwing it out. Tell me, heliocentric model, because these words mean something. So just what does that word mean? That's what's stumping you? You just remember heliocentric, but you don't know the meaning of the word? Go ahead, tell me. What does it mean? Okay, good. So Philip, that the Earth and the planets orbit the sun, not the other way around. Why was this so important? Because prior to the work of Copernicus and Galileo, it was believed that geocentrism was the case. And geocentrism holds that the Earth is at the center of the solar system and cosmos, and everything revolves around the Earth. Now, why was it so important for early generations of the West to believe that the Earth was at the center of everything? Well, they thought that that was necessarily true because they assumed that if God created the world for the sake of mankind and we're created in his image, then we should be right in the center, because wouldn't we have the most important position in the universe if everything was created just for us to live here? So a religious orthodox doctrine was that God would not have put the planet Earth in a random, non-central position. But now we have people that are emerging with newly invented telescopes like Copernicus and Galileo, and they're discovering that actually, based on observation, you can tell that we are not at the center and that we do orbit the sun. So anyway, his discovery of heliocentrism, replacing geocentrism, was widely thought of as like a revolutionary result because it opened the door for further scientific investigation and knowledge to replace whatever had been ecclesiastical lessons where the church was dominant before that. Another important figure in the early history of Western science is Sir Francis Bacon. We talked about him too. He lived from 1561 to 1626, and he was a British philosopher and a statesman, and he discovered and wrote about the steps in the scientific method. So that's his legacy that he left behind. The scientific method we'll talk about in more depth today, actually. We're going to go through all the steps piece by piece. But it's basically a procedure where you start by observing facts, you try to give an explanation or a hypothesis to explain why, and then you try to test that hypothesis to see whether it is correct or not. That simple procedure, which has led to the development of all kinds of technologies, medicines, transportation, communication, you name it, that's made our human lives so much better and more easy to deal with. It all kind of goes back to the scientific method, so we have a lot of, I guess, gratitude towards him for that. Now, afterwards, and then, hey, good to see you too, Carson, and Nathan, or sorry, I meant to say Matthias, thanks. Afterwards, we talked about what are some different assumptions that are behind science, so like fundamental baseline assumptions that science as a field has to and does make. One of those assumptions was the idea of empiricism. And once again, that's just the belief that the five senses are the primary source of human knowledge. So most human knowledge comes from the five senses and what we can observe. That's a fundamental assumption of science, which is crucially observation-based. Another major assumption of science is what they call objectivity. And this is the idea or belief that we can learn about the universe as it really is, not just as it somehow appears to be, but as it really objectively is. And that we can get to that objective truth with no bias or, or some type of skewed, slanted, biased perspective. So according to objectivity, this world that exists is not just something made up by your head. It's not made up in your mind. It's an objective world out there. And there are objective facts about it that are just waiting for us to discover. So according to science, we hold out the hope and the belief that there are the possibilities of discovering objective truth independently of our own personal biases or assumptions. Another assumption of science is what they sometimes call materialism. Others call it physicalism, but in our book they called it materialism. Let me ask you that. Who could tell me what the word materialism means in a scientific or philosophical sense? Yeah, definition, materialism, what's that one? Not the common definition of it that you see in pop culture, but the sort of scientific meaning. So let me hear that one from you, anybody. What is materialism, the assumption of science called materialism? In other words, what's being assumed in materialism? So just takes a moment, to go back in your memory or look at your notes or open that book again. But you'll get it, and then we'll be able to say something about it. But I'm just touching base with you. So let me know. Materialism. Anybody? What is that? We learn about diffusion of responsibility, right? Where you're in a group and you think someone else will do something, so nobody does it. Maybe that's how you're feeling right now. You're like, well, whatever, there's 11 of us. Let me let some of the other ones try and answer this. They see when that happens, nobody does it because everyone's thinking the same thing. So you got to be the one individual. Okay, there you go, Matthias. The only things that exist are physical objects and phenomena. Pretty much, yeah. So that's one way to put it. I believe that we put it, the way we put it is similar, but a slight different wording. And then what you have, Lan, the belief that everything in the universe is made out of physical matter, including us and our consciousness. Good. So those are both the right statement. I think that yours is more fulsome, Lan, because it talks about one important concept within materialism, which is that even the mind, even your mental life and your thoughts, your feelings, your emotions, your memories, pain, pleasure, all that stuff is also just physical. According to materialism, it's all just made out of atoms, really. Atoms, which are these tiny little particles of matter, they combine to form all the objects around us, including us ourselves. So if you're a materialist, you think that consciousness is just another physical process playing out. It's not like a soul or a ghost or a spirit. It's just a physical brain with neurons and synapses, and that's the seat of consciousness. And if there were no brain that were able to function or to exist, then consciousness would go away with it because it's a physical thing. So that's materialism. A scientist assumes that everything's made out of matter, everything's physical, there's nothing that's supernatural or that's outside the range of atoms operating according to the laws of physics in the void of space. Now, another assumption of science, aside from that, is what they call predictability. Predictability is the assumption that the universe as a whole is orderly and predictable. And that means that if we have determined what a cause-effect relationship is in nature, then that would be permanent, stable, and it would hold forever. It would be repeatable forever. So predictability. The universe overall is orderly and predictable, so established cause-effect relationships will be repeatable and will hold forever. I tried to explain that by means of this little example of me holding a marker like that. And I said, if I open my hand and let the marker go, what do you predict would happen? And you guys were able to make a pretty reasonable prediction that it would fall, just like that. But if I asked you, and I did, I followed up and said, well, why do you think it's going to fall? What made you so sure? And after a moment of thought and reflection, you're like, okay, I guess it's because of gravity, right? But then I didn't let it go. And I'm like, well, how do you know gravity is going to keep working, though? I mean, what you're saying is gravity is the reason that you think it will fall. But we haven't been to the future yet, so how do you know gravity won't just stop all of a sudden now? And at that point, all you can really say is, well, I assume, don't I, that gravity is not just a temporary thing, but it's permanent, and it's a phenomenon that would continue to function in the same way for all eternity if I had enough time to keep dropping this marker forever. So that's the assumption of predictability, that the natural laws that govern how things work in the world and the universe, that they never take time off, that they never stop, and that they will never change. So if gravity is the reason this happens now, then a scientist, and I guess you also assume that that law of gravity is not just for now or here, but it's for all time and for everywhere. Okay, so natural laws are permanent and durable for all time, according to the assumption of predictability. And another one that we talked about was the assumption of unity. And hey, good to see you, Jordan. The unity assumption was simply that scientists assume that there's an underlying unity to the overall universe, such that everything could be explained according to a single set of scientific laws and principles. This is a goal, the grand unified theory, an elegant set of physical principles that could explain everything from the largest to the smallest events. But as of today, we haven't gotten there quite yet, because we have two different fields of explanation for two different scales of reality. We have quantum physics for the tiny little quantum scales, and then we have the theory of relativity for the larger macroscopic big picture scale. And we have not yet been able to build a bridge between the two fields so that they are consistent with each other. So hopefully as the 21st century continues, we'll get to our grand unified theory, but it's an assumption of science that it's possible. Okay, after that, there was some discussion last Thursday about what are some limitations of science, some limits that science faces, things that I guess maybe we can say it's not able to either prove, or assumptions that it makes which cannot be absolutely vindicated. One of them was the idea that science assumes the existence of the external world outside of your mind, which of course is a widely shared assumption by everybody, but it's something that you technically can't prove, because if you were living right now in a dream or a simulation, then the simulation, if it was very good, would be just exactly like this, and therefore you couldn't distinguish it from reality. So unless you're Descartes or some kind of Cartesian skeptic or a solipsist, then you probably don't have any problem assuming that the external world is real and it's not just an invention of your mind. But anyway, if that's a limitation of science, I guess then it has that limit. It has to assume the existence of the external world, which we can't absolutely prove. But I don't find that to be the most difficult limit for it to face, because nobody really takes skepticism that seriously. Another assumption, or limit I should say, of science was it's only about things that can be observed. So science can only discuss or talk about things that can either be directly or indirectly observed. So if there were anything that was unobservable, then it would always remain outside the scope of scientific analysis. So, I mean, dark matter, if that's something that cannot be observed, then scientists will have a very hard time discovering much of any important insight about it. Or if there are such things as the supernatural, the paranormal, souls, angels, ghosts, God, if any of those things exist, then by their very nature, they would be outside the realm of what you can observe through your five senses. And therefore, if they did exist, then science would not be able to explain them or talk about them. So science, another possible limit is that it's only about the things that are observable. And some people also critique the assumption I mentioned just before of predictability. Like some people will claim, how can you really know for sure that the natural laws will never vary or change into the future, since all we've had experience of so far is the past up till the present? Once again, it's a core assumption that these laws are permanent and immutable. But maybe some people like David Hume, the British philosopher of the 1700s, think that that's an assumption that you really can't help yourself to. Okay, now from there, as I finish off the review portion of this early part of our meeting, I want to ask you this. What were different views that were expressed about the relationship of science to religion? So let me know if you remember any of those. In the book, they say that when it comes to science and religion, sometimes they don't see eye to eye. Sometimes they appear to disagree. And what are different attitudes that some can have in the light of these disagreements between science and religion? So let me hear about it. Different views regarding the relationship of science and religion. Even if you have even one of them, let me see it in the chat, and then I'll go over it. So, when science and religion disagree, okay, good, Philip. Some will say that science should be given priority when there are these conflicts. Okay, so if science says man evolved from great apes and it took billions of years, and religion says, no, God created us in his image within 7 days, that does not look like agreement. That looks like one is saying something different from the other. And if you're holding this view, that you favor science when there's disagreement between them, then you would say, I'm going to hold the scientific explanation to be the correct one, and I just reject the religious explanation. So that's one attitude. Another attitude, a good land, is the reverse, which says that religion takes priority over science when the two conflict. So in the same example, if someone heard that there was a biblical flood, but scientists say no, there's no meteorological way that that could have happened in that part of the world at that time, then the person will say, you know what, the scientist must be wrong because I claim that the religion is true. So if there were a religion that said that the earth was only thousands of years old, but science says, no, we have fossils that prove that there's been life on this planet for millions of years, then the person with the second view would say, I'm going to go with the religion claim and reject the scientific view. A third view, okay, good, Lan, could be that science and religion are dealing with different topics, so there's actually no real conflict. And some people say that. Some people will say that of science, it's about the physical world, and it's about cause and effect, and about laws of nature. So you might say science is about an objective physical reality, but religion is about a subjective spiritual reality, like a world where we talk about morality and our values. So if that's the case, then maybe they don't really disagree because they're just in their own different lanes. When you're doing science, you're doing nothing that conflicts with religion and vice versa, because one is about the subjective and spiritual and one is about the objective and physical. Perhaps, although as I said before, this perspective is sometimes hard to sustain when you just look at the obvious fact that there do seem to be straight up disagreements between at least some scientific and religious claims. Now, what is a fourth view? I don't think I've seen this one there yet, but there is one more. Did we talk about the fourth one? I think so. Let me see if you know. Number 4, yay, nay? There you go. Thanks again, Lan. So science and religion are compatible. That's another possibility. Some may say that if you simply interpret the religious claims or doctrine in the right way, then in that case, they may actually come into alignment and agree with what scientists say. Like in one example, the Bible in Genesis says that God created the universe in 7 days, and on the 7th day he rested. But science tells us that no, it took billions and billions of years for the aftermath of the Big Bang to result in gaseous material coalescing into stars and then planets forming, and even longer for life to evolve to the stage that we are at now. So how can those two things be made compatible? Maybe a person would say that, well, in the Bible, when it says there are 7 days of creation, it didn't really specify how long a day was. So that could be a long, era of time, and it's just arbitrarily designated as a day to make sense to the readership at the time. So in this way, we're trying to reinterpret or expand on the interpretation of the religious message so as to bring it into conformity with whatever the scientist says. And you say here your question, you could also say that a lot of religious ones are metaphorical, perhaps, right? So sometimes biblical stories, parables, you might argue that they're really just trying to teach you a lesson and that they don't necessarily have to be considered literally true. So the Garden of Eden, this would be another example. According to the Bible, God created the first 2 human specimens in this paradise type setting of Eden. But of course, according to science, no way that, there's no single two human beings at the initial outset of humanity. There's just a bunch of specimens coming from the large process of evolution that generated us over a long-standing period of time. So is this another case where we see this disagreement? Maybe you can claim, well, it's a metaphor. The Garden of Eden is just a metaphor trying to tell you, like, not to disobey the word of God or to not give in to temptation. But it didn't necessarily literally mean that, yes, there were actually physically just one woman and one man at the beginning, or that she was made out of his rib or something. But at any rate, to sustain this last view that they're compatible because religion is just making metaphorical claims and stuff, you know, you would have to kind of always be willing to revise a religious claim or interpretation whenever a scientist discovers something that is in contradiction to it. So it might start to appear after a while as a little bit ad hoc, like you're just doing whatever you think is necessary to keep your religious views intact. Okay. Now, from there, we're going to go on, and we have to now talk about the steps of the scientific method. Before I launch into each of the steps, I want to describe something that the textbook talks about, which is how there are similarities between the steps in the scientific method and the steps in the critical thinking process. Okay, so when we put the header here, similarities between the scientific method and the critical thinking process. Okay, so if you remember going way back to the earlier parts of our semester, we talked about the critical thinking process as happening in a series of discrete stages, three precise stages. So the first one was experience, which leads to interpretation, which finally gives way to analysis. Experience, interpretation, and analysis. These are the three steps of the critical thinking process, critical thinking, CT. And now, how is that somehow similar to the scientific method? SM for scientific method over here. Okay. Now, we're going to go into full-blown detail about the scientific method. What I've noticed in life is this. This scientific method is, in different textbooks, sometimes described as having a different number of steps. I've seen it simply stated with 3 steps, which is like the core minimum. And I've seen as many as 5 steps, which is what our book uses. And in other cases, I've seen like 4. So although there's these differences between how many steps are usually given, in every case, there's a minimum of 3. And the big 3 kind of match and pair well with the 3 steps of critical thinking. So here they are. In the scientific method, you start off with observation. You know, you just observe some event or phenomena in the world. And that's kind of like experience, because as we know from experience, you begin the process of critical thinking by just describing what happened, either to you or in general. But at that first stage, you're just saying what happened. You're not yet trying to describe or explain how or why, just what happened. So like, I got fired, but you're not yet trying to understand the reasons behind it. Just that's what happened. Similar over here, you start by observing the world and noting some kind of event or phenomena that happened. But with the scientific method, you have to move on from that to try and start explaining the event, what the cause of it could have been. So that takes us to step 2, which is hypothesis. Okay, so observation, then hypothesis. By the way, I don't know if it's like audible to you, but there's like a little noise pollution just because of some construction work that's happening. They're replacing some wooden railings around outside of my, house here. So sorry for that. I'm trying to talk over it, and for the most part, just try to ignore it if you can, if it comes up. Of course, now it's getting silent, so it's kind of ironic. Anyway, observation goes to hypothesis. So a hypothesis is an educated scientific guess to explain the occurrence of the observed phenomena here. Oh, thanks. Thank you, Glenn. So we start by observing a phenomena that happened. Now we're trying to give our explanation as to why. And that kind of mirrors how we try to interpret the reasons behind the experiences that we have when we critically think. Finally, the last stage of the scientific method is to test the hypothesis. Okay, so we put the hypothesis to the test. We perform an experiment which can result in confirming the hypothesis or disconfirming the hypothesis. And how is that similar to the critical thinking procedure? Well, in the same way over here, you have an experience, you try and then explain why or how, but you allow yourself to come back to the interpretation later to see, is it really the correct one? So the analysis stage is basically where you consider, is this the right interpretation? And you try to judge that. In the same way, a test puts the hypothesis to the test. This test is given to try and evaluate whether this is the right hypothesis or not. So if the test verifies it, great, maybe you have the right explanation. But if it doesn't verify the hypothesis, then that sends you back to creating another one. Just like if your analysis seems to indicate that your initial interpretation was wrong, now you're going to try and come up with a different interpretation for the same phenomenon. So critical thinking and science have similarities. Science is just a little more formal and procedural, but in our everyday lives, when we're thinking critically and trying to understand why things are happening, we're kind of reasoning in the same way that scientists do, by identifying the event, trying to explain the reasons behind it, and then evaluating whether that explanation is even correct. Same over here. We observe events, we create a hypothesis to explain their occurrence, and then we'll test the hypothesis, and maybe the test will show that it's right, or maybe the test will show that it's wrong. So this kind of reconsideration of the interpretation that happens here is kind of like the scrutiny that the test applies to the hypothesis. Okay, and good to see you, Anna. Not to worry, but better late than never, as they say. Better late than later. So there we go, similarities between the scientific method and the critical thinking process. But what we now have to do is zoom in on the details about what the scientific method is and all 5 of the steps that the book calls out. So let's go into it. So now what we are discussing is the scientific method in specific. The scientific method, first formulated again by Sir Francis Bacon. Okay, so what's the first step? It's labeled in the book, identifying the problem. Identify a problem. So I'll put it like this. Observe the world and identify something that you don't understand why it happened or what caused it to happen. So an unexplained phenomenon. Observe the world and identify an unexplained phenomena. That's the first step to identify a problem. So science is all about offering explanations for things that we observe, right? But you have to have something to explain to get the scientific procedure started. So if there's no problem to solve, then there's nothing for science to do. So the first step then, in other words, is to just look out at the world and see something that has happened that you don't know why. In ancient times, it could have been people look up at the sky and they see an eclipse, and they're like, what? There shouldn't be darkness at this time of day. So this is something I don't understand. I've noticed something blocking the sunlight. So initially, it's just something that is waiting to be explained. There is an explanation, but earlier generations of humans didn't perhaps know it yet, what the explanation was. Or you see lightning out there, and prior to the discovery of electricity and how it works, maybe people were just mesmerized. Like, what is that? I mean, I'm seeing it, but it's not explained yet. Coming into a more modern context, okay? Let me give you an example that's also used in the book, so it's helpful to touch base with that. Right now in the world, globally, there seems to be a general decline in the number of bees that we have, the bee population. In fact, it's become such an issue that they've coined a phrase for it, bee colony collapse disorder. And bees actually play a pretty important, significant role in the health of the biosystem because of the role that they play in, pollinating flowers and such. So it's a concern that they're declining, but that's something that we see. We just observe the world and we see this as a measurable fact that there's a decline in the overall number of bees. to be fair, it's not even limited to bees so much. This issue has started to be noticed with other animals, or I should say insects, in the insect world. So we're seeing like butterflies and other kinds of insect life declining in general, which is a worry. Anyway, you have identified a problem, but science doesn't just say, hey, there's something we don't understand and that's it. There's obviously more steps. So let's talk about the next step to follow afterwards. And this is a very important step because it is when you create the hypothesis. So step 2 is to develop an initial hypothesis. Okay, develop an initial hypothesis. So let me make sure we all understand for sure what a hypothesis is. This word, what does it mean? A hypothesis is just an educated scientific guess to explain the occurrence of an observed problem. So it's like the scientist trying to reasonably assess what could be the basic reason for the observed phenomena that you saw at step 1. Okay, so one develops an educated scientific guess to explain the occurrence of the observed problem. Or we'll say phenomena. Okay, so initial hypothesis. Like, for example, why could possibly these honeybees be declining in numbers? So let's just work with that problem and see what possible hypotheses there could be. Not to worry, good to see you, Oliver. Good, welcome back. So in relation to bees declining in their global numbers, maybe one hypothesis could be this. We see this phenomena kind of traced to the early 2000s and into the current day. Maybe because around that same time, like cell phone technology was becoming more widely deployed. Maybe the reason that bees are declining is because cell phone tower radiation and frequencies are somehow interfering with their life cycles, migratory patterns, or reproductive success. So could it be, just one possible educated guess to explain the declining numbers of bees, could it be the proliferation of cell phone technology, which is correlated with the onset of the bee colony collapse disorder? Maybe so, maybe not, but it's a hypothesis at least. What could be another one? Maybe somebody might think changing global temperature from climate change has some kind of measurable effect on the bee colonies, and that's causing their collapse. Or maybe the introduction of new types of insect species that are preying on them, and this type of species, locusts, wasps, I don't know, are overpopulating and thus eliminating bees. Or what? Is there some new pathogen that's causing bees to get sick? Another possible hypothesis. So anyway, you have a hypothesis, you've developed it, it makes an attempt to give the explanation for the observed phenomenon. But that's not where the method stops. We continue on to step 3. Now, I was saying before that in different textbooks, the scientific method is sometimes divided into a different number of steps. I've seen it 3, 4, and in this book 5. This third step is one of the ones that I would argue is more like optional than some of the others. But it's interesting, it's important, and I think it's worthy of notice. So let's add number 3, which is this: to gather additional information and refine the hypothesis if necessary. So putting it here, gather additional info. And refine the hypothesis. Okay, so say you had observed some fact or a phenomena that you want to explain. So that was step 1. Then you gave your initial hypothesis to try and explain that thing, why it happened, or what causes it. Now you reach step 3. What step 3 involves is sometimes you have to edit your hypothesis just a little bit or make it a little more specific or narrow. You might have to make little tweaks or adjustments to it based on your initial data collection. So you have a hypothesis and you're collecting information and data to try and get ready to test this hypothesis, but that might sometimes force you to make slight revisions to what it says, to what your hypothesis claims. Like, here's an example. You thought that bee colony collapse was happening because of cell phone tower or radio frequencies that are being emitted into the Earth's atmosphere. Suppose you start trying to research this question in preparation to test it, but then you start to notice that it's not every frequency of cell phone radiation that seems to be having this adverse effect on bees, but just certain frequencies like 5G or something. So now what started off as cell phone radiation is harming the bees has been made more narrow and specific to 5G cell phone radiation is harming the bees. Or here's another possible example. So youth depression and suicide rates, sorry to say, they're actually a lot higher for the Gen Z cohort than they were for the millennials or for before that, like Gen X. And that's a problem. You know, what could possibly be the reason that a lot of young people right now coming up, teens and stuff, are suffering through more depression and higher rates of suicide than we might have seen in the past few decades for people at that same age? Maybe a hypothesis that a person has is because people growing up now that are young, like Gen Z, they're all growing up with social media. So some people might think that early childhood exposure to social media, comparing yourself to other people, trying to get followers, likes, and all of that could be causing some people to fall into greater depths of depression and, you know, not being mentally as happy or well. But suppose that as a person starts to research the topic and they're looking at different demographics and suicide rates and internet access and what apps people use, they start to notice that it doesn't seem like just every social media site is leading to this phenomena, but just the photo sharing social media sites like Instagram or whatever. So now the person's hypothesis maybe gets modified. What started off as social media engagement is leading to greater teen depression has been narrowed to social media engagement with photo sharing sites where people compare the way they look to others and stuff and try to flex and pose for the camera. Maybe this is causing more people to feel lesser than others or, you know, outside of the mainstream, and that's leading to more depression. So I don't know, I'm just giving you a couple of grab bag of examples about how to think about this. So gather additional information and refine the hypothesis. Here we can now fully define that. Refine the hypothesis if necessary, or I can say adjust the hypothesis if necessary. Based on your initial data collection. So there's been a lot of school shootings and mass shootings over the past 22 years, more so than there were in the 22 years before that. Maybe somebody thinks it has to do with gaming, but then they narrow it down to certain types of game or a certain genre of game, and they think, okay, like early childhood exposure to first-person shooter games perhaps has this kind of correlation. I don't agree with that at all. I think that actually can be disproven if you compare access to these games across cultures, and you see that the rate of like mass shootings are not the same in some cultures which play games even more. But anyway, in every example mentioned here, the common theme is that you start with a hypothesis which has to be kind of adjusted or tweaked, edited just a bit to make way for the initial information that you learned from collecting data. In the book, it says all this. It says, the initial hypothesis may be modified on the basis of further observation. Since we can never be certain that our hypothesis is correct, collecting information is an ongoing process in science. And you should not be so committed to your initial hypothesis that you refuse to edit it or modify it based on initial data collection. So confirmation bias should not allow you to reject any information that seems to discredit your hypothesis. Okay, now what about step 4? We're getting to step 4, which is all important. Step 4 is one of the big ones, and that is when you finally test this hypothesis. So now you have your narrowed down hypothesis, which is all in its final form. And now you can finally go forward to test it. So that's step 4, test the hypothesis. Test the hypothesis. So basically now you're ready to conduct an experiment which will either verify or disconfirm the hypothesis. So here we go, either in a real world or laboratory setting, one conducts an experiment that will have one out of two possible outcomes. So there's either the successful or the unsuccessful outcome of the experiment for your hypothesis. You'll conduct an experiment that will either confirm the hypothesis or disconfirm it. So that will either confirm or disconfirm the hypothesis. So you have to test your hypothesis, and you know, it might be that after you do an experiment, you'll find that your hypothesis has been verified. But in other cases, you know, you'll find that the experiment shows your hypothesis was wrong. It's not the proper explanation for the observed phenomenon. So in that case, well, we'll talk about that in a moment when we get to step 5. But let me ask you a quick question. So suppose that you're the scientist and you were going to go out and try to study in this question. The question being, or the hypothesis being, that cell phone tower radiation maybe is what's killing off a lot of the bees around the world. So if that was your goal or your research project, tell me how you might design an experiment. Like, what would be the experimental design to test the hypothesis that bees are dying off from cell phone radiation? I mean, when you do a test, an experiment, you usually have a variable that you can control, and you see whether or not it has a predicted outcome. But let me ask you, just think about it for a moment and then say what you can in the chat. Question, how do you test to see whether these bees are dying off from cell phone radiation? How could you possibly test for that? What might be the way of doing it? Just to make sure that we all understand the way that tests are performed on a given hypothesis. So let me ask you, and let's see what you think. Just take some moment thought. But imagine that you're going to try and actually do a test. You're going to run an experiment. How could we run this experiment? The experiment is going to check whether or not cell phone radiation really is killing off bees, or if it's not doing that. We know they're declining in numbers. Maybe this is what's causing it. But to test it, how do you think we could test it? So just let me know. Okay, so good, Philip. You're saying this. Have one group of bees in a room with something that emits this type of radiation, as the cell phone towers do, so just bombard them with it, and have a second group that is in a normal environment. Okay, good. So the dependent variable is exposure to the cell phone radiation. And you have two groups. You have a test group and a control group. The test group is the one that you're going to expose to the variable, expose them to the cell phone tower radiation, and make sure that the other group is completely prevented from any similar exposure. Now, according to the hypothesis, which says that they're probably dying because of the radiation exposure, if that was the correct explanation, then what's the predicted outcome of this experiment, right? So tell me what would happen in the experiment if this verified the hypothesis. What does the hypothesis predict in relation to the results of the two groups? If this really is having an adverse effect on bees, then according to the hypothesis, what should we see in the end? We should see that with what? You should see a higher rate of decline in the test group. That's right. So if cell phone radiation is interfering with the life cycle or whatever survival rate of bees, then when one group is exposed to a lot of it and the other isn't, we should see that the group with the exposure is dying off as predicted by the hypothesis. So we run the experiment, and it might be that the experiment shows that there is a relation between the two things, or it might show that there's no such relation. So suppose you run the test, and as predicted, the radiation exposed group is dying off in big numbers and the other one is doing fine. Now you might say, you know what, I think I got it. I think I explained it because the sample group that was given the radiation, just as I thought, they're declining. So that might be the real reason that we see this phenomenon in the world. On the other hand, though, you might run the experiment and you don't see that it confirmed your hypothesis. So you expose one group to radiation, not the other, and you see no difference in the two. Or maybe even the one with radiation is getting stronger. I don't know. I don't want to make it too complicated, but let's just go with no difference between the two. If that was the case, then you cannot say your hypothesis was validated by your experiment. It seems like the experiment shows that it was falsified. And so that means you got to go back a little bit to a previous step. So finally, then we get to the last step, which is 5. Okay, so step 5, the final one, is this. You're going to now evaluate the hypothesis based on the testing results. Okay, so here's the basic idea of this. You've completed your experiment to test your hypothesis. Now you're going to look at it, as I just was kind of hinting with the previous example, you're going to look at whether or not the predicted result of the hypothesis is what the experiment showed. So that would be confirmation, but otherwise the experiment shows disconfirmation for the hypothesis. And that means there's 2 different possible results: success, or your hypothesis was unsuccessful. So if the hypothesis was verified, if the experiment confirms the hypothesis, okay, so if it confirms the hypothesis, then in that case, publish the results for further replication by other scientists. And on the other hand, if the experiment disconfirms the hypothesis, then I have a little question for you. I'll hold you in suspense for a minute. If the experiment disconfirms the same hypothesis, then in that case, go back to, okay, now I'm going to ask you this. Suppose that you got the disconfirmation result. So you thought it was cell phone tower radiation, but you pumped one room of bees full of the radiation and not the other, and it's doing nothing to them. There's no measurable effect at all. So that doesn't show that radiation's probably the cause of their decline overall. That means that you got to go back a few steps. So which step do you go back to, you think, if your hypothesis was disconfirmed? Going back in the order of steps, which one will it return you to? And then repeat. So think about it, but let me know. Having not confirmed one hypothesis, you now return to the prior step called which step? Exactly, Philip, correct. You're going back to step 2, meaning you're going to develop a new hypothesis, because you still haven't explained why these bees are dying. So we're still waiting for our answer. We're still waiting for the right explanation. One hypothesis was tested, but it failed. And so if it does fail, you have to keep trying to develop different hypotheses until eventually one has successful confirmation by an experiment. Okay, so then go back to step 2 and repeat. I mean, that's kind of cramped at the bottom, but I'll read it just so that it's unambiguous. It says, if the experiment confirms the hypothesis, then publish the results for further replication by other scientists. Okay, just let me say something about that first half here. Say that, as it might have been, that your experiment confirms the hypothesis about the bees or whatever. So cell phone radiation into one group, not in the other control group, but the test group, they're dying off in big numbers. So you might be like thinking, okay, I think I have the right explanation. So you would publish those findings. You'd publish the scientific study. And you would say, hey, world, look, read this published study where we did our scientific research. And we discovered that when you expose a test group of bees to cell phone tower radiation, it shows that they start dying off. This might be the explanation of the global phenomenon called bee colony collapse disorder. Now, other scientists in the scientific community, in their own research institutions and using their own materials, are going to try and replicate the findings. And when other scientists find the same results and we all kind of converge on the same results, then after a while we say we think we actually have the right explanation. But as I noted, if you get disconfirmation from the final result of the experiment, then you have to go and try and come up with something else. So in that case, you'd think, I guess it's not cell phone tower radiation. What could it be? So you switch to some other explanation and repeat from there. I'll read a little from the book on this point. And here's what it says. It says, the last step in the science method is to evaluate the hypothesis using testing and experiment. If the results or findings do not support the hypothesis, then scientists will reject it and go back to step 2, come up with a new hypothesis, and repeat. The scientific method is ongoing. Old hypotheses and theories may be revised or discarded in light of new evidence, or replaced by hypotheses with greater explanatory power. After 4 years of research into the cause of honeybee colony collapse, a 2010 study at Penn State College of Agriculture found unprecedented levels of a particular pesticide chemical in honeybee pollen and hives. However, this hypothesis, while one of the most promising, has yet to be fully verified. The current hypothesis has been expanded to include multiple causes, including new pathogens, bee pests, environmental and nutritional stresses, and pesticides. So anyway then, that is just an example that I use to draw you through the steps in the scientific method and to see how a concrete example could be compared to these definitions. Next thing I just want to say really briefly is this. I want you to know the relationship between a scientific hypothesis and a theory. Because these words are oftentimes mixed up with each other and they are similar, but there's one crucial difference. A theory is just a very well-proven hypothesis. It's a hypothesis that's been put to the test over and over again, and it seems to be validated each time. So theory is just a well-proven or well-established hypothesis. So what starts off as like a hypothesis that's more tentative and subject to elimination or revision, once it's in a final form that is verified, not just once, not just twice, but over and over again by a wide variety of people in slightly different conditions, then we say it's starting to graduate to the status of theory. So it starts as a hypothesis, but can become a theory if it's repeatedly verified. And we think of theories in science as like our closest approach to objective truth. Since science is all based on induction, even very well-proven theories still remain open to possible revision in the future. But we think that they're much less likely to be invalidated because they've been proven so much over time. So like widespread theories that we think are like core facts about reality have survived the gauntlet of experimental testing that makes them credible. Okay, so then having talked about the full scientific method and all the steps, we are next going to speak about what the book calls qualities of a good scientific hypothesis or theory. So we want to be able to tell the difference between a good, credible scientific hypothesis or theory and something that is not. And since not all theories or hypotheses are created equal, some are better and more capable of explaining the phenomena than others are, we want to be able to know what sort of parameters make a hypothesis or theory a good one as opposed to a bad one. So here's the heading. It's just qualities of a good scientific hypothesis or theory. Okay, so the first one that is mentioned in the book is relevance to the problem being studied. In my view, this one is like so obvious that it almost really didn't need to be mentioned, but I guess since the book mentioned it, I'll talk about it with you too. Clearly, a hypothesis is not good if it's not relevant to the thing that it's trying to explain. Like, imagine that you're trying to explain something physical or meteorological by a hypothesis that has something to do with something sociological. That would be totally a mismatch. Like if I say to you, okay, hurricanes have been increasing with their intensity and number during hurricane season in the last 20 years. So we seem to be having more intense periods of hurricane in the that part of the year than we did in the 20 years before that. What about that? Why is that happening? Why are we having more intense hurricanes? That's a problem, say, that one wants to explain why. Suppose their hypothesis is, well, we've seen divorce rates like skyrocketing during that time. So maybe because 50% of people that get married are going to get divorced, and that's happening at around the same time that the hurricanes are getting worse, we see the correlation, maybe that's causing it. But that would be a bad hypothesis that you could simply dismiss, because it's trying to explain something that happens in terms of weather with sociological facts about people making up and breaking up. And the two things, we cannot see any kind of relevant direct connection. So some hypotheses are just weird and wild. They make claims, but they're not even relevant to the subject matter of interest that you're trying to explain. So one baseline quality that a good hypothesis or theory has to have is it has to be in the same related ballpark of the problem that you're trying to study. Okay? And it says that in the book. A good hypothesis or explanation should be relevant to the problem being studied. In other words, it should be related to the phenomenon that it is intended to explain. Okay. Next, we're going to talk about the second of these qualities, which is consistency with other well-established theories. Okay, so let me explain with a little brief definition or whatever. What this is about is that a good scientific theory or hypothesis, it should fit in with, and it should not contradict, other very well-proven theories that have come from before. So, a good hypothesis / theory should fit in with and not contradict other well-proven theories. Okay, so you've got a good hypothesis, it's going to fit in and not contradict these other theories that have been well-proven. So let me give you like a little bit of a mental picture to think of. Consider like a metaphor that science, in a way, is like a big jigsaw puzzle. And so if there's a new theory that arrives, it's supposed to fit into that existing puzzle. It's not supposed to be oddly shaped so that you would have to actually throw out other pieces to make a way for it. So science is supposed to be a body of information that all coheres together, that all works together as one coherent explanation and one coherent body of scientific knowledge. Sometimes in science they use this statement or saying that new scientific research in the modern day is standing on the shoulders of giants that have come from before. So scientists believe that when you have new theories that emerge, they should fit into and they should be built on top of what has already come before, that they should not clear away and reject prior scientific theories that have already been well proven and well established. So a good scientific theory is not going to force us to reject other extremely well proven things that we think we already know. It should just build on top of them, but not force us to reject them. Let me give an example of a hypothesis that would not satisfy this requirement, and that would mean it's a bad hypothesis. It's a little bit of a silly example, but just let's roll with it, okay? So say when you get up on Christmas morning and you look under the tree, you see there's gifts. And so you're like, wow, gifts are under the tree. I wonder what caused that. And suppose that, maybe you're like a young child and you think, I believe Santa Claus is the real reason that these gifts are here. So my hypothesis is that Santa came and delivered these gifts to me last night, and that's why they're now here in my tree. So your hypothesis for where the presents came from is Santa delivered. But let's go into the Santa hypothesis a little bit more in depth. There's all kinds of stuff about this Santa myth that would contradict clearly understood principles of science if it was true. Okay, so if Santa really is the one that delivered you these gifts, first of all, according to the legend, he's transporting around on a reindeer-driven sleigh that flies through the air. But that would violate all kinds of things that we know about principles of aerodynamics, physics, and biology, because reindeer are terrestrial life forms that don't have any mechanism by which they could fly. And to propel something up into the air, you need to deal with forces that a sleigh driven by reindeer cannot generate. So unless we don't know what gravity really is, or biology, or aerodynamics, then this is not even possible. So for you to hold the Santa hypothesis, you would have to reject fundamental core principles that we already have well proven in other fields. So that's why it's not the best hypothesis, right? Because it doesn't fit with all this other stuff that we think we already have proven. Now, are there ever exceptions to this rule? Sometimes, but it's rare. Once in a blue moon, very rarely, there could be a revolutionary scientific hypothesis that does actually force us to reject things that we thought we knew from before. One example of this is the work of Albert Einstein and the theory of relativity. It forced us to make slight changes to what we thought we knew from Newtonian physics, from the work of Isaac Newton that came like 300 years before Albert Einstein. But Einstein's work was overwhelmingly supported by evidence, and it was able to issue much more accurate predictions than the Newtonian principles were. So once in a while, when you have an overwhelming set of evidence and no other viable explanation for it, then that can force like a revolutionary change to a paradigm that we thought we had. But that's the exception rather than the rule. So for the most part, with those revolutionary exceptions aside, a good scientific hypothesis or theory will arrive to the scene and fit in with the other stuff that's already been there from before. Let me read from the book on the same point, and here's what it says. Science is a system of logically consistent hypotheses or theories. So scientific explanations are preferred if they are consistent with well-established theories in the field. What American historian of science Thomas Kuhn refers to as normal science. This system forms a paradigm or a particular way of looking at the world. For example, the new hypothesis that internal processes in the ocean, such as the release of oceanic methane that exist on the seafloor on continental margins, are the primary cause of global warming, is considered a good hypothesis by environmental scientists, since it is consistent with the established paradigm that global warming is a result of man-made and natural changes in the earth. The intelligent design theory, on the other hand, this is all from the book, does not meet this criteria because it is inconsistent with the well-established theory of evolution. So in judging the credibility or quality of a scientific hypothesis, you should consider whether or not it fits in together with other things that we already know. And if it doesn't, then that might be a reason to suspect that it's not correct. Okay, so we continue from there. The next one is called simplicity. Now, the simplicity criteria for a good hypothesis or theory is sometimes labeled with another name, and it's sometimes referred to under the heading of Occam's razor. So I'm going to put that in parentheses here just so you know that that's another possible label for this, Occam's razor. And why do we have that other name? Because this principle was first kind of argued about and discussed by a medieval philosopher and theologian named William of Occam. So William of Occam, he's famous for the Occam's razor concept, which our book somewhat more minimally just also refers to as simplicity. Now here's the idea that I'll put below. The concept of Occam's razor, or simplicity if you want, is that when you have different explanations for the same event, say you have two different possible explanations, explanation 1 and explanation 2. They're different, but they're both trying to say why something happened. If one of the two of them is simpler than the other, it involves less assumptions than the other one, it's less complex, then that one is likelier to be true. So the point is this: the simpler out of two possible explanations for something is the one that is likelier to be true and correct. Okay, so is likelier to be true. So the simpler out of two, likelier to be true. Okay? Now, I'll try to make this clear enough by giving you a little example. Okay, so suppose that you parked somewhere with your car, And you know, you get out and you go and you do whatever you're going to do. You come back to where you had parked. But when you come back, you're a little bit sad and upset because you notice this. Your car's not there anymore. It's not where you parked it. So that's a problem. And at that point in time, you're going to become like a miniature scientist, I guess, and you're going to start thinking, okay, well, what's my hypothesis? What could have happened to it? You know, you got a problem you're trying to solve by giving an explanation. So who could tell me what might be a reasonable, common sense explanation for that event? Say that your car wasn't where you had parked it behind. Now it's not there. What would be an initial educated guess to explain this fact? You know, this has actually happened to me, so I don't know if it, maybe most of us hasn't happened, but whether you can relate or not, just imagine that. What could be an explanation for that? Explanation for what? For not having your car there. Okay, so you're saying gotten stolen or towed. Two different explanations. That's fair enough, Philip. Sure. You might think, okay, well, maybe my car was stolen by somebody, and they took it away, and that's where it is right now. That's why it's not here. That could be an explanation. Another possible explanation, as you said, could be the towing hypothesis. Maybe the reason that it's not here is because it was actually in a designated spot it's not allowed to be, and that caused a towing service to take it away. Now, let me work with the towing hypothesis just for the sake of argument, and let me compare it to another one, all right? And I'm going to make a different one that's a lot different. So suppose I give you these two explanations to choose from. Maybe it was towed, that's one hypothesis. Or on the other hand, maybe aliens came down from outer space and they just take my car back to wherever their spaceship is, and you know, they wanted to abduct it so they could like learn more about human, I don't know, technology. So now I'm giving you those two. Towing or aliens came down and took it. Now I'm trying to make this one real easy for you guys. So let me know. Which of those is simpler? You know, which one involves less assumptions? You don't have to assume all this extra stuff to sustain one of the hypotheses. But for the other one, you have to make all kinds of kind of weird and wild additional assumptions. But which one is simpler? You know, I gave you the two. Towing is way simpler, correct. It's just a much more straightforward and simple hypothesis. What additional assumptions do you have to make to support the alien hypothesis, as opposed to the towing, or I guess Anna stolen? I was going with towing, but it's fine. To sustain the alien abduction thing, you have to make all these extra assumptions that you don't have to make to just assume it was towed away. So then, what are these extra assumptions that are, you know, based around or built into the alien hypothesis of the event? I mean, you'd have to assume, first of all, that what? To suppose that aliens took your car, you have to assume all kinds of stuff. Like you have to assume things that you don't know, like what? Now I'm asking you this question. What are the assumptions that are built into that complicated hypothesis that's not simple? I mean, it's easy enough, right? You have to, first of all, assume they exist in the first place, right, Philip? Which is not a known fact. I mean, maybe there's aliens in outer space, but for now, all we know is that there's human beings and other life forms on Earth. So you have to assume, first of all, that there's life in outer space. Second of all, you have to say that, yeah, that they know about humans. Not only that, okay, you'd have to assume there's alien life, but not just that there is alien life, but that it's highly intelligent. Because if there's alien life that's coming to visit us from another planet, you know, somewhere in the solar system or somewhere out in the cosmos, then these are aliens that have mastered the ability to travel through space and to arrive at the planet Earth. Human beings haven't even ever touched down on another planet. So these would be aliens that are not only existing, but highly intelligent and more advanced than us. And then we would also have to assume that they take an interest in your car, of all things. So look, maybe that's a hypothesis, I guess, but it's not the best one when you compare it to the other, because it's way more complicated and there's way more assumptions that have to be made to stand it up. And that's what scientists as a general thing believe, that when you have two hypotheses that each try to explain an event, assume that the one that is simpler, that holds less assumptions, is true. And I guess metaphysically, you know, philosophers and scientists assume that the universe overall is elegant and it's parsimonious, which means that there seems to be a preference that reality has for the simpler of two possible explanations. Now, that's probably why, like, people say, you know, conspiracy theories and stuff are usually less likely to be true than the official story, because you have to make a lot of additional assumptions to sustain the conspiracy theories that don't need to be made when it comes to just the official story. So anyway, yeah, keep that in the balance of factors. When you look at a theory or a hypothesis, if there's another one that could explain the same thing, which is simpler, it's probably likelier to be true. And here's what the book says. It says if rival hypotheses or explanations both satisfy the other criteria, scientists generally accept the one that is simpler, a principle known as Occam's razor, named for medieval philosopher William of Ockham. The great majority of scientists reject intelligent design theory because, among other reasons, the theory of evolution is simpler than intelligent design, because evolution can explain the gradual development of complex organs such as the eye, beginning with light-sensitive cells that primitive organisms possess, and there's no need to assume the existence of a supernatural being to add to the process. So like the, creationism versus evolution hypothesis, I guess you could argue that the creationism hypothesis is less simple because it posits the existence of a supernatural being in a realm that somehow has a connection to the natural world. But on the evolution hypothesis, you only have to assume what we think we already know, that there is a natural world that operates according to certain principles of natural selection. Okay. At the same time, I want to say this. It's not impossible for the more complex theory to be accurate in some cases, but as a general tendency, the simpler of two is likelier to be true. Okay, so we go on then from there. Next, we're going to talk about what's called falsifiability. Falsifiability. Okay, now it might sound a little odd to you, but it is a good thing. It is a good thing when a scientific hypothesis is somehow able to be proven false. Because if there's no way to prove that it's false, then there's no way to test whether it's true either, and that means it's unscientific, because everything that's scientific has to be capable of being tested for whether it's true. So falsifiability. It is when a good scientific theory is capable of being proven false. Good scientific theory is capable of being proven false. Okay, so think about what it is to test a hypothesis. Like going back to our bee colony collapse thing about the cell phone tower radiation. If that was your hypothesis, it is falsifiable. The hypothesis that cell phone radiation is causing it. What would falsify that is if you do the experiment and then you don't see it having any effect on it. That means, never mind, that wasn't the proper explanation. But that's falsifiable, which is good, because if it wasn't no way of falsifying it, then how could we test it? To test something means you're looking for whether an instance of falsification happens or not. So in the advance of the experiment, you say, here are the two possible results. Confirmation would be this result. Disconfirmation, falsification, would be this other result. But if you don't even know what falsification would be, then there's no way to determine whether or not you got it. And therefore, there's no way to see whether you had confirmation either. So unfalsifiable claims are not scientific because there's no way at all they can be tested. Take, like, for example, like the horoscopes and astrology. This is pseudoscience. It's not real science because it's not falsifiable. If you read the astrological report and it says something vague and ambiguous about what might happen to you in the next week, like say, oh, you're going to be visited by an old friend. And then, you're like, well, nothing happened actually, so that was falsified. The astrologist is not going to say, never mind, I guess I'm wrong. They'll just say, no, you're not paying close enough attention to your own life. You maybe didn't notice the friend that came to visit you. Or maybe it meant something metaphoric, like a little bird perched on your balcony and was singing to you in the morning. And that was the friend that came to visit. But look, what will never be conceded by the astrologist is that anything counts as falsification. And so that means they're also not offering you any form of experimental verification. They don't say, look, don't take my word for it. Perform an experiment on your own. And maybe if this happens, that means that my claims are false and you can test it for yourself. So they don't offer you any ability to test it. They just say, take these as givens and nothing can falsify them, because even if you think you have falsification, it doesn't count as falsification. Now that's like with astrology and pseudoscience, but even in certain fields within the academy, we've seen unfalsifiable and therefore unscientific claims. One example could be the work of Sigmund Freud, famous, sometimes called father of modern psychology and psychoanalysis. He had a lot of interesting ideas, but some of his stuff was weird and wild and not scientific, probably because he was doing a lot of cocaine, to be honest. Back then, cocaine was in a lot of consumer products, including Coca-Cola, so not everybody knew how dangerous and harmful it could be. But anyway, he was using it a lot, and he just thought it was increasing the quality of his thought and like making him more stimulated to his work. But yeah, he had some weird ideas. Like one of them was this. So he thought that little children were all like proto-sexual, meaning that little boys have a latent sexual attraction to the mother, and he called that the Oedipus complex. And he says that when a boy becomes an older person, they'll seek out some partner that reminds them in some ways of their mother. And he thought the same of little girls, that they suffer, well, not suffer, but they have the same condition of what he called the Electra complex. So they have a latent sexual attraction to the father figure, which plays out in adult life as they seek a partner that has some similarities to the father. But if you disagree with Freud's analysis here, and you say, no way, that's just weird. Little children are not sexual beings yet, and they're not thinking of their parents in a sexual way, and certainly I wasn't. If you say that to a Freudian, then Freud's response is this. Well, of course you don't think you have those thoughts because you submerge them into your subconscious. And so, of course, you're not going to be able to detect whether you had these thoughts or not. But that means that nothing I say or do can possibly count as falsification for his theory. If you tell him there's no evidence of your theory, he will say, well, you shouldn't find evidence because it's in the subconscious. And since things that are in the subconscious can't be directly observed, that's why you can't falsify my claim. But that means it's not scientific. So here I'll read from the book on that. It says, a hypothesis or explanation should be presented in a form that is testable. In addition to being testable, it must be able to be falsified. One of the main tasks of the scientist in testing a hypothesis is the search for negative falsifying instances. For example, the hypothesis that all swans are white was based on observations of hundreds of thousands of swans, each one of which was white. However, that was falsifiable since it would take only one non-white swan to prove it's false, which eventually happened when black swans were discovered in Australia. On the other hand, theories that are able to accommodate all challenges have a critical weakness because they cannot be tested for whether they're false. For example, Sigmund Freud's theories about the Oedipus complex fail the falsifiability criteria, since if a man claims he does not have this complex, Freudians argue that he has repressed it into his unconscious. However, unconscious thoughts are not testable, and therefore there's no way to falsify his theory. So anyway then, make sure that you're looking at scientific claims that provide at least some method by which they could in principle be falsified. And here's the last thing I'll say about this. To be falsifiable does not mean that it is false, nor does it mean that it will be proven false. It just means that we understand the condition that would have to happen if it were false. Okay, so like some people might think, isn't it weird? I mean, how can being falsifiable be good? I thought the whole point was to prove they're true. It is. The point is to prove that the hypothesis is true. But again, you can't gain any kind of experimental confirmation of it if you don't even know what to compare confirmation against. Disconfirmation. So there has to be a condition for falsification for it to be a real scientific claim. Okay. And then the one more and the last quality of a good scientific theory that they mention there is just predictive power. And that is easy to explain, so I'm just going to do it quick. This is when a good scientific theory is capable of accurately predicting future events. Is capable. Maybe I'll say this, because then it sounds like the theory is doing the prediction, but it's you who uses the theory. So let me say this. A good scientific theory can be used to accurately predict future events. Good scientific theory can be used to accurately predict future events. Okay, so you know you have a good scientific theory when it can basically tell the future. That's one of the main reasons we like to have this scientific knowledge, whether it's the property of certain chemicals, medicines, natural substances, or physical phenomena. Having a good theory allows us to tell what's going to happen based on the knowledge that we have discovered scientifically. So think about how when there's a solar or a lunar eclipse, astronomers know well in advance the specific date and time that those eclipses will happen. They can even tell you the exact place on the Earth's surface where you should stand to have ideal viewing conditions. So then when the eclipse happens at the exact predicted date, according to the theory, that offers us confirmation that this is a credible body of scientific investigation, because when it makes a prediction, then it happens. I can give you other examples. Think of meteorology, the science of weather. When the weatherman makes a report that you should bring an umbrella on Saturday because there's a 90% chance of rain, and then it rains, we see that the meteorologist is not just making wild guesses or has a hunch, but that this is based on sound scientific principles that can issue accurate predictions. Is it 100% accurate in every case? No, but it's more reliable than not. And so anytime that a scientific theory allows us to make accurate predictions of the effect of certain outcomes, then that's another basic reason to grant credibility to that theory. So good scientific theories are relevant to the problems that are being studied, consistent with other well-established theories. They're the simpler of all available explanations for the given problem. They're capable of being falsified, which means they can be tested, and they can make accurate predictions of related phenomena in the future. Now, there's only one last thing in chapter 12 that I do want to say before I let you go right now. And so let me just briefly say this. Pseudoscience, what is that? So pseudoscience is like fake science. The word pseudo literally means false. So pseudoscience can be called fake or junk science. The book defines it this way. It's a body of explanations that wants to look scientific, but it actually isn't. So it is a body of explanations that, as they put it, masquerades as science. To masquerade, their verbiage, is to like put on a mask that will cover your appearance and conceal it from others. So what the definition is, what the definition is saying is that in pseudoscience, there's something that wants to like appear as though it's based on scientific principles and some kind of rigor, but in fact, it's not scientific because there's no actual tests that are involved. The predictions they make are stated in vague and ambiguous language, and they're not falsifiable claims either. So what are some realms of pseudoscience? Here are some to just give as a little laundry list. You've got astrology, numerology, like thinking that numbers have some kind of mystical significance, psychics, tarot card reading, crystal ball gazing, and we could go on and on and on. So in all of these pseudoscientific fields, like sometimes people say, oh, I'm like a ghost hunter, and they bring some kind of weird tool to like a haunted house. Oh, there's high level of paranormal activity detected by this device. In all these cases, they try and make it seem as though their field is based on like a wide wealth of scientific research and investigation. But as I say, you can tell that they're definitely not scientific because they don't offer you any theoretical like experimental proof. They don't say, the astrologist doesn't say, look, conduct an experiment to see whether or not my claims are true. Or here is some peer-reviewed research which can demonstrate that these things are falsifiable and that they happen under controlled conditions. All you have to do is simply conceal the name of the astrological sign on a chart and try and pick out which one is actually yours. And you'll see that it's not so easy to do. So I'm picking on astrology a little bit, but it's the same with all. And so let me read the last thing here, just a quick quote from the book, and then we'll be good for today's meeting. It says, pseudoscientific explanations involve no tests or experiments to check out their validity. The few studies that are carried out are generally poorly designed and cannot be repeated. And they try to explain the failure of their explanations to stand up to scrutiny by blaming the subject. So it's like, oh, if you say that you can't see the ghost, they'll say, well, you just don't believe enough. And so there's no way you can falsify the person's claim. They also fail to meet the criteria of predictability because they're so broadly worded that just about anything could bear out their predictions. Despite the lack of scientific legitimacy, belief in pseudoscience is widespread. So let's try not to be so gullible as to offer our support to pseudoscientific fields that really don't have our own best interests in mind. The people that are peddling this information are always just trying to make money off of you by offering you some kind of new age solution to your problems that you really cannot have. That's about it, guys. That's all I have time for today. So let's make sure that you're ready on Thursday to take your quiz on Chapter 12. It just has to do with all the information presented in these last two meetings, today and Thursday. So you can use the book, use the notes that you've taken, and your good common sense, and you should be fine. But we won't have a lecture on Thursday, just the quiz, and then we'll return next week to finish up with the one more chapter, which is Chapter 9. So if everything's good to go, then I'll let you guys go. Thanks for submitting your homework the other day. I'll be grading it through the weekend, as well as this quiz that you're about to do, and that should be all ready within the next week. So are we all good to go then? Let's see. If so, then I'll close the stream, but I just want to give you a chance to say goodbye before I do that. Okay, thanks so much, Anna. Appreciate it. To all the others, Matt, thanks again. Lan, Brittany, good to go. All right, well, have a good one, and if you need anything, I'll be in touch by email. Other than that, good luck on the quiz this Thursday, and I'll see you guys again not too long. All right, bye-bye.